There we go. Okay, so you've been dealing with polygons for a long time. You've known what those are since probably elementary school. We've talked about what inscribed means. You learned that a little bit last year. We kind of reviewed that last week. And that's one of the first warm-up questions here. It says, what is the difference between circumscribed and inscribed? So could you, in one or two words, describe what inscribed is and what circumscribed is? Try circumscribed first. Keely? Which one's inside? Inscribed means inside, okay? So inscribed means we're making something inside another figure, inside a circle, inside a polygon, or something like that. When you hear inscribed, just think, hey, we've got to have something inside, okay? So what do you think circumscribed would mean? Wilson?
The outside.
It's going to be on the outside, okay? We're making something on the outside. Okay, now there are some special rules about that, like it's got to touch the vertices or got to touch the circle and different things like that. But if we say something is circumscribed, that means it's on the outside of whatever the figure is. If we say it's inscribed, that means the figure is on the inside of whatever it is, and it's normally touching the edges or the vertices and stuff like that, okay? All right, if three angles of a triangle add up to 180 degrees, which we all know is the triangle sum theorem, we've talked about that numerous times. You learned that in 7th grade math, if not in 6th grade. Then four angles of a quadrilateral add to, do not say anything out loud, I've got some hands up already. Any old quadrilateral. Triangles are easy, but if I just draw a quadrilateral over here, something like this, if we add up the angles on the inside of that quadrilateral, how many degrees would we have? Okay, Luke had his hand up first. Luke, what do you think?
360.
It is 360. Can you tell us why?
There's probably a fancier reason, but I took a square, which is everyone's favorite quadrilateral.
Absolutely.
And then I took two triangles, I put them inside the square, and I realized that was 360, and that applies to all quadrilaterals for some reason. It
actually does. So we're going to take what you did and we're going to modify it a little bit. He took a square and he just chopped it in half and said, well, there's a triangle over here and a triangle over here, so 180 and 180. But it doesn't make any difference. So if I were to take that ugly looking quadrilateral and just draw a diagonal and break it into two, the upper one is a triangle, the lower one is a triangle, and each one of those have 180 degrees between them. So if we take this angle here and that angle right there, adding those two pieces together, if I add up all those angles, I'm going to get 360 degrees altogether. So the interior angles of a pentagon, so that's going to be 5 sides. Well, mathematicians are pretty good at saying, hey, this worked before, let's try it again. Didn't we just draw any random old quadrilateral? So draw a pentagon. Luke, what was your trick with the square?
Draw triangles inside.
Yeah, draw triangles. So could we take that pentagon and could we chop that up into a bunch of a bunch of triangles? Draw one here and draw one here.
540.
So how many triangles do we have? We have 540 triangles. We have 3 triangles, each with 180. So, Sai, how many degrees? 540. So 540 degrees in a pentagon. Hexagon. Okay, Dane, do you think it's 720 or do you know it's 720? He thinks it's 720, okay? So if I were to draw a hexagon, 1, 2, 3 diagonals take care of it. There's a bit of a pattern as to how many sides there are and how many triangles you can make out of that and how many diagonals you have to draw. Okay, so that would be 4 triangles, right? Each 180. So 4 times 180 is 720, okay? So a formula for an n-gon, and again, don't say anything, let everybody figure it out. So an n-gon just means this is how many sides it has. So we could call a triangle a 3-gon. We could call a quadrilateral a 4-gon. A pentagon would be a 5-gon. A hexagon would be a 6-gon. So what if we just said it's an n-gon? It has n sides. Could we come up with a formula that tells us how many degrees there are on the inside? Three sides, 180. Four sides, 360. Five sides, 540. Got a bunch of hands up. Samara, what do you think?
I feel like 180 times the n-gon.
Okay, 180 times the n-gon. So I'm going to put 180 on the end here, and I'm going to do the n. You want me to just put an n?
I put the whole thing.
Okay. Oh, the n-gon, the whole word. Okay, we're close. N is the number of sides. We're really close on this. Keely? Not quite half of n, but you're on the right track.
N minus 2.
N minus 2. Okay, so if you take the number of sides and subtract 2, that will tell you how many triangles you have. So if you have a 3-gon, you've got 3 sides. Take off 2 from the number of sides, you've got 1 triangle. If you've got a 4-gon, if you've got a quadrilateral, take off 2 from the number of sides. You've got 2 triangles. 2 times 180 would be 360. It works all the way on up. Okay? So you can do n minus 2 times 180, or you can do 180 times n minus 2. Doesn't make any difference because of the commutative property of multiplication. Yeah.
Could you do like n times 180 minus
360? Yes, you could. Okay. If you wanted to, you could do this. 180 times n and then subtract 360. That would work just fine. Okay. All right. Everybody good? Okay. Whichever one you like, that's totally fine. So, as we've mentioned before, and we're going to mention a couple times today, if we know a bunch about angles and sides and chords and arcs and stuff like that, we can figure out a bunch of other stuff. So our goal today, again, was this. Our goal is to be able to figure out missing angles of inscribed polygons. So we're going to come down here and we're going to take a look at this. And this is a theorem. So this is example 1. And for example 1, we're going to do a proof. But luckily, there aren't a bunch of proofs on your assignment. We're just going to go through and we're going to see if we can take something that should kind of make just common sense, and we're going to see if we can come up with a proof for it. And notice that most of the steps are there. They're almost filled out for you. Okay? So it says, here's the theorem. If a quadrilateral is inscribed in a circle, so it's inside the circle, the vertices are touching the edges, its opposite angles are supplementary. So that means this angle right here and this angle right here. A and C would be supplementary, which means they add up to 180 degrees. Every single time, if you've got a polygon or quadrilateral that's inscribed inside a circle, the opposite angles are always supplementary. They always add up to 180 degrees. Okay? Can anybody think of a reason why that would be true? Okay, I'm going to draw a line from here to here. Can anybody think of a reason why it would be true? Smart, what do you think?
Like if you fold it in half, basically, it would be like they'd be the same. Like they both have to equal. I don't know how to explain this.
Yeah, you're on the right track. Yeah, so we could kind of fold it together. They both kind of be like half of something. You're on the right track, Si? You're right about that, but I haven't drawn a radius on here, and we wouldn't be able to depend on that. Jack?
If you like bisected that both B and D, then that means they're the same on each triangle. So that means the A and C are the same.
If it was bisected, that would be true. Okay. So let me ask you this question, and then that'll kind of lead to the proof. Okay. So over here, I've got an arc, right? Let's call that X. What's this one?
Y.
Could be Y. But why would I want to introduce another variable if I know around the entire circle? We did this last time. If one of them is X, yeah.
Oh, it could be like X2.
It could be X2, but that's a different variable if we use subscripts. Luke?
360 minus X.
360 minus X. We're taking advantage of the fact that the two of these add up to 360 degrees. So this would be half of the arc that it intercepts. Remember, we talked about that earlier. Half of the arc that it intercepts. That would be part of the 360. Then the other one would be half of this arc. That would be the other part of 360. So if we're taking half of 360 altogether, how many degrees do we have? We've got 180 degrees altogether, okay? So let's run through this proof here. So here's the quadrilateral. It's ABCD, and it's inscribed in circle E. So again, the circle is named by the center, okay? And the reason for that is that's given. They told us that. Okay, then it says, and take a look at the way these arcs are written down. This is arc BCD plus BAD. So BCD, so that's this part right here, and arc BAD equals 360 degrees. Well, yeah, that chops it into two pieces. That's the entire thing. What we call that is just arc addition. The fact that you can add them together and get the whole circle. So I'm going to erase that and look at the next one. This is the same reason, but we're looking at different arcs. Arc ABC, so ABC is this one, added to ADC, that's this one, they add up to 360. So kind of what Samara was talking about, it's kind of each of one of them, it's half the circle-ish, okay? Maybe a little bit more than half, maybe a little bit less than half, but the two of them make up a full circle. Everybody good with that? Okay, next one. 2 times angle A, so angle A is right here, equals the measure of arc BCD. So it equals the measure of this arc right here. Now we've got 4 statements. We're just going to look at them one at a time and kind of reason ourselves to a couple of them. Is that statement right there true? Is twice the measure of angle A equal to the entire arc? Yes, because the formula we use is this. The inscribed angle is half of the arc, right? So if we just multiply both sides by 2, we'd get the full arc equals double the angle. We okay with that? We'll look at one more, so I'm going to erase this stuff. The next one says, I'll just pick one randomly. I'll pick this one right here, the one on the end. Angle D, so 2 times the measure of angle D. So we're talking about this one right here. Whoops. 2 times the measure of angle D is the measure of arc ABC. So this one right here. Is that true? Yep. Because normally the inscribed angle is half the intercepted arc. So if we double the angle, we'll get the entire arc. Everybody good there? Okay, so we're done with that one. So we're going to say the intercepted arc is blank, the measure of the inscribed angle. What do I put here? Double. Yep, double or twice. Either one's fine. Okay, next statement. 2 times the measure of angle A plus 2 times the measure of angle C equals something right here, and it gives a reason. The reason is substitution. So take a look. 2 times the measure of angle A plus 2 times the measure of angle C.
360.
Yeah.
360 degrees.
It is 360 degrees. It's 360 degrees. So here's what we've substituted for. We've taken this one right here. So here's arc BCD. Arc BCD is 2A. So I replaced this one with that right there. Arc BAD, that's right here. I replaced that with 2C. Okay? Everybody good with that? What do we do here? What changed from here to here? We're taking baby steps. We're justifying what's going on. Factored out the 2, factored out the, I'm going to write GCF. Okay, if you want to write 2 in parentheses, that's okay. I'm going to put Caleb on the spot. Caleb, what do we do from here to here?
You just divided 2 from each side.
Yeah, divided 2 from each side. Does anybody remember how to finish this off? That's the division property of equality. So you can just put an equal sign right there. Okay. And then the very last thing is, well, that means that A and C are supplementary because they add up to 180 degrees. And B and D are supplementary because they add up to 180 degrees. And that's by definition of supplementary. Now, remember, if you get to a point where something is basically, well, no, duh, of course that's the case. If we're making a statement like they're supplementary coming from this, well, of course they are. That's usually a definition. Not always, but it's usually a definition. Okay, any questions? Okay, Let's be clear about what this means. So look up here for just a second. This angle and this angle are supplementary, always. This angle and this angle are supplementary, always, because it's a quadrilateral inscribed inside a circle. Okay? So all we have to do is look at this and say, hey, what's going on here? Do we have a quadrilateral inscribed inside a circle? Yep. So if this is 80, the one straight across from it has to make up the difference between that and 180 because it's got to be supplementary. So Andy, what's this one right here? That one's going to be 100. So we got 100 degrees right here. And if this is 120, the one across from it's got to be supplementary. So Jack, what's this one?
60.
That one's got to be 60 degrees. Okay, any questions?
Yay, Dad.
Okay, pretty easy, right? Okay, flip the page over. We've got a couple problems that we're going to run through.
No.
Now, remember, if you know a little bit about chords and angles and arcs and inscribed polygons and circumscribed circles and stuff like that, you can take one tiny piece of information and you can figure out a whole bunch of stuff. So it might be good, rather than just looking at it and saying, hey, how can I apply this theorem? Could you figure something out that you already know? Okay, so I'm going to zoom in on this one just a little bit. We've got an inscribed quadrilateral. It says that inside that circle A, the center's A, arc EF is congruent to arc FG. EF congruent to FG. And it says find the measure of each numbered angle if angle 1 is 12x minus 8 and angle 2 is 3x plus 8.
Wait, isn't it?
Hang on a second, let everybody think. Does anybody notice anything about this? Huge advantage right here. Has a name. Can you give me the name of what I just drew?
Yeah,
What's it called?
diameter.
It's called the diameter. Diameter cuts the circle in half. If it cuts the circle in half, take a look at this one up here.
90.
What is it?
90.
Yeah, it intercepts an arc. So this is 2 halves of a circle. There's 180 degrees over here. So this has got to be a 90-degree angle. And this one over here is half the circle. So this one's got to be a 90-degree angle. Huge piece of information just by recognizing that that's a diameter. Now, I'm going to point to these guys right here. Point to those congruent arcs. If those are congruent arcs, even if it doesn't look like they are, what do you know about those 2 angles? Keely? They don't have to be, between the 2 of them, they have to be 90. You're right about that. But if this arc is congruent to this arc, what can you say about what is it? The 2 angles are the same. And if we've already used 90 degrees between these, I've got 180 minus 90. I've got 90 left to spread between the 2 of those, and they've got to be equal. So what's the measure of angle 3 and angle 4? 45 degrees. So divide by 2, we get 45 degrees on this one and 45 degrees on this one. So 45 degrees here, 45 degrees here.
Don't we know the measure of angle 1 and angle 2?
We will.
Oh, but it's just 12x minus 8.
It is, but we need to figure out what x is. And we use something very similar to what we just did. Zach, what'd you do?
I took the 12x minus 8, and then I combined that with 3x plus 8, and then the 90. So
And the 90?
yeah, plus
Okay,
90 equals
plus the 90 equals
180.
180. Now let me just point something out here. What he did is he took angle 1 plus angle 2 plus the right angle right here, and it equals 180 degrees altogether. Now, if you wanted to cut to the chase just a little bit, we could say, hey, there's 90 degrees here, so between these 2, there's got to be 90 degrees. We could have just added those together and set them equal to 90. Either way, correct me if I'm wrong, 15x, the 8's cancel, equals 90, so x is equal to 6. And it says find the measure of each angle, so then we've got to plug it back in here. So 12 times 6 72
-8.
minus 8, 64. So angle 1 is 64 degrees. And then we could either do subtraction from 90 if we wanted to and figure it out that way, or plug it in here. 3 times 6, 18, plus 8 is 26. And do these two angles, do they add up to 90 like we thought what they would? They do. Okay, let's slide down here. Okay, now, let me just point out, I realized after we made the notes that there wasn't one asking about an arc. You've got a couple problems on your assignment that ask about arcs. Okay, so let's take a look at this one. The measure of angle NML is 80 degrees. NML, so this entire thing is 80 degrees. The measure of angle N is 40 degrees. So this is 40 degrees. And it says find these measures right here. Let's see. Got an idea? Lizzie?
Well, 40 is an inscribed angle, so you can figure out what the arc of OL
So
is.
this whole thing would be 80. Okay, so that whole thing would be 80. Can we do the same thing over here?
Yeah.
Yep, that whole thing. And I'm going to change colors just so we can keep these straight. I'm going to mark that as 80. So from here to here would be 160. Yeah.
I know what N and M are.
You know what N and M are? What do you mean? Oh, you mean this arc right here? Okay, what is that arc?
120.
I
Wait.
don't think it's 120 because we've got this overlap here. I don't think you can say for sure. Okay, but you can say this. Remember what the theorem is. Remember what the theorem is. If this is 40 right here, and this is an inscribed quadrilateral, that means this one over here is 140. It's that simple. They're supplementary, so that's going to be 140. If this one here, I'll change colors again. If that whole thing is 80, what's this one over here? Okay, I'll do this so we don't think that they're congruent. This one's going to be 100. Okay? So, do we have the measure of angle NOL? NOL, yep. 100 degrees, right? NOL. If this is 80, that's got to be supplementary to it. Okay? Don't get distracted by that line in the middle. That's just extra. That's not part of the inscribed quadrilateral. Then I need angle L, 140. Okay? And then did we figure out what arc NOL is? NOL? 160. Okay? All right, everybody good there? I know you didn't have arc NOL on your paper, but go ahead and put that there. Okay, got it? Okay, a couple more. Find the measure of each numbered angle for the figure, and it says arc JK is 120. Arc JK is 120. Do we know anything else? Samara.
Well, KL is 60.
KL is it? Okay, I think it is, but how do you know it is? Zach.
JL is the diameter.
JL is the diameter?
Which means
Exactly. Yep. That's what we're looking for. So Samara's right. This is going to be 60. Okay. Let's talk about these numbered angles then. If we've got the top looking like that, hey, wait a minute. If the top looks like this and this is perpendicular, what does the bottom look like? Yeah, it's the same thing. So we'd have 120 here and we'd have 60 here. Can anybody tell me what angle 1 is? Doesn't matter what order we get these, but can somebody tell me what angle 1 is? You don't think so?
Oh, it's 60. Wait, it's 30.
Why? Why is it 30?
Because it's inscribed.
It's an inscribed angle, and an inscribed angle is half of the intercepted arc. So if it intercepts an arc of 60, this has got to be 30 degrees. And if that's 90, the one over here is 90, that's 90, that's 90. So we've got that going for us. Take a look at angle 2. It's the same type of thing, intercepted arc of 60. So that means the angle's got to be 30. And then there's a bunch of different things that we could do here. But if this is 90 and that's 30, I've used 120 degrees altogether. So can somebody tell me what angle 3 is? Crew?
60.
It's got to be 60, okay? And if we wanted to, I could do something like this. That's the right angle because it intercepts a diameter. So this has got to be 30 degrees, which makes this 60, which makes this 60, which makes this 30, and makes this 60. Everybody good there?
Yes.
Take a look at it. Again, think about some of the stuff that we were doing when we were solving quadratics and the part of our brain that we were using then. This should feel like a completely different part of your brain, and look at the tiny piece of information we have. We knew that that was a diameter, and we knew one arc measure. That was it, and we filled in all of this. Okay, any questions? Okay, slide down, take a look at the last one. Huge, huge piece of information here. They didn't say it, but you can tell it by the way it's drawn. Dane. There's a diameter. And Dane, if this is a diameter, can you tell me one of the angles? Don't. 2 is 90 degrees. This is a right angle right here because it would intercept half of a circle, a semicircle. So it's going to be half of that. It's going to be 90 degrees. And then it says angle R, which is angle 3. This is half of x. And angle K is 1/3 x plus 5. Okay, so I'm going to ask Zach, what do you think would be the best way to figure out what x is here so we can figure out what the angles are?
Just add them all together and equal them to 180.
We could add them all together and set them equal to 180. Or, since I already know I've used 90 right here, what could I do?
Oh, you could just do them equal to 90.
Very good. Equal to 90 and then solve from there. Can somebody raise their hand and tell us what is probably, not the only way, but probably the easiest way to solve this? It depends on how much you like fractions. Samara, you want to take a stab at it?
Well, I was gonna say something else.
Okay. What were you going to say?
Well, I was gonna ask if you could just do, since that one's 90 and that whole thing is 180, the other two would be split in half, so those would be 90, and then you could just do inscribed from those.
45 and 45 or something like that. Unfortunately, we don't know where P is. P could be anywhere around here. It's a good idea, but it wouldn't work in this case. They'd have to give us some more information to know. Okay? You can solve it with fractions, or could we clear fractions if we want to? What could you multiply by that would cancel off a 3 and a 2? 6. We're going to clear the fractions by multiplying both sides by 6. So here's what happens. It cancels here. We get a 2x. We get plus 30. We get plus 3x. And then on the other side, I've got 6 times 9. So that's going to be 540. So I'm going to have 5x. If I move the 30 to the other side, that's 510. And I'm really hoping that that goes in there evenly. It's 510. It ends in a 0 or 5. So it's going to go in there evenly. So what's x?
102.
X is 102. Now, x is 102, but it doesn't say find x. What does it say? Find the measure of the angles, correct? So you got to plug them in here. So we've got, this would be, I'm going to change colors, 1/3 of 102 plus 5. And this is going to be 1/2 of 102. So half of 102, that's going to be 51. So angle 3 is 51 degrees. I already got angle 2. That was 90 degrees. And this other one had better work out to be 39. Does it work out?
Yeah, it does.
34 plus 5, right? Okay. All right. Would you fill out the self-assessment about how you're feeling about that right now?